right, so let's look at number 13. So this is from 20.3. So looking at number 13, what are we doing with our two radical expressions? We're multiplying them. So when we multiply radical expressions, everything that's not inside of a square root, what do we do? Number 13. So, yep. So we have 4 and 5m are not inside our radicals. So we multiply them, right? Just like we would any normal numbers. We're going to take 4 and 5m, and we're going to multiply them together. Which is, so we have 20m. All right, so now we're left with our radicals, right? And our radicals, they're both cube roots, correct? So the houses, quote houses, are the same. They're both cube roots. So since they're both the same index, then what can we do with everything that's inside those radicals? We have two houses that are the same. So everything that's inside, we can combine them. We can put them together. So this 4m squared and 2m squared are both inside a cube root. So we can put them inside one big cube root. All right, so now let's multiply some numbers. So we have this 4, correct? Can we factor tree that? Yeah, let's do that. Since this is a cube root, we want groups of how many? 3. So 4 factors to 2 times 2, right? So we can write this as the cube root of 2 times 2, and I'm going to bring this 2 since it's a number there. And m squared, how else can I rewrite that? Well, I can write it as m to the 4th, but if we were to take m to the 4th and do a factor tree for it, all right, so now we're looking for groups of how many? 3. So 3 on the inside makes how many on the outside? 1. So I have 3 2's here. So those 3 2's make how many on the outside? 1. I have a group of 3 m's here. So those 3 m's make how many m's on the outside? 1. All right, so now I'm going to rewrite it up top here. So we have 20m times, what were we able to pull out? 2m. And then what's left inside our cube root? Just this one little m over here. We didn't have any friends to help escape. So everything that's outside our radical, what can we do to that? We can multiply it. So 20 times 2 is just rewriting it as a group. So 20 times 2 is 40, and m times n is m squared, and then we have the cube root of m. So this whole thing rewritten is 40 m squared times the cube root of m. All right, easy enough, just like that. All right, so now let's look at 14. So let me clear. Yeah. Because our index here is 3. On a square root, what's the index? 2, but we don't write it. And no, it's good questions. Better to ask now and know than to think you know and get it wrong later. All right, so number 14. So here now we're dividing, right? We have 2 times the square root of 52x to the 9th divided by the square root of 13x. Is 52x to the 9th, is that a perfect square? No. Is the square root of 13x, is that a perfect square? No. So instead of taking the square root separately, what can I do to that 52x to the and 13x. I can divide them. I can put them inside one square root. So this 2 is going to stay on the outside. And then I'm going to put one big square root with 52x to the 9th divided by 13x. Now, what is 52 divided by 13? You guys have calculators? I hear guessing, but no. Okay. So we have 2 square root 4, and how many x's? I have x to the 9th divided by x. X to the... So we're subtracting. So this has a 1 here, so 9 minus 1 is 8. All right, so now this is a square root, so I need groups of how many? 2. So 4 factors to 2 times 2. And then 8x, I can rewrite that as 8x's being multiplied together, right? All right. So now, doing our groups of 2, I have 2 groups of 2 here. So 2 2's on the inside makes how many on the outside? 1. Then I have this group of 8 x's, this group of x's. So how many groups of x's do I have? 4. So times x. Let me rewrite this multiplication like that. All right, so x times x times x times x. I'm going to pull those out. So when I do that, I'm pulling out x to the what power? To the 4th. So now on the outside I have my original 2 times 2 times x to the 4th. And what are we left on the inside? Is there anything left? No, so I don't have to write the square root, right? I have 0 left inside. So this simplifies to what? Good. All right, so now thinking about how we did number 13 and 14, looking at number 15, it says, what conditions must be satisfied for a radical expression to be in simplified form? Well, what are we doing here when we circle our groups? We're combining, we're finding groups that match our index, correct? So here we didn't have anything left inside, right? So it was in simplest form. In the previous one, we had, I guess I erased the answer too. We had an m left inside in number 14, right? Why couldn't we simplify that any further? Right, because we didn't have any full groups left, right? We didn't have a full group to pull out. So when you're looking at putting it in simplified form, like how would you explain that to a student who missed that lesson or didn't completely understand it? How would you explain that simplifying process? What are you looking for? What are we doing? All right, so you're looking for groups of numbers that match the index. And so how do you know when to stop simplifying? What do you no longer have inside that group? Groups, full groups, yeah, that match that index. So if you have your index of 3, you're simplified when you have no more groups of 3 to pull out. All right. So questions on that one? So now we're going to move into 21. So next we're going to look at geometric sequences. So this is on page 313. And we're going to identify geometric sequences. So our learning targets today, we want to identify geometric sequences and the common ratio in a geometric sequence, and distinguish between arithmetic and geometric sequences. All right, so why don't you read that top paragraph, and that kind of gives you the background. We're going to be dealing with, I guess, emails and how things can go viral and what that means. Like, what's happening mathematically when, things go viral. So read that. All right, so we're multiplying by 3 to the previous stage. So we have 1, and then we're multiplying it. Keisha's sending it to 3 people. Each of those friends are sending it to 3. So that's where we're getting this table from. All right, so use the table that I used to graph the viral video situation. So let's look at, we're just going to do the number of people who are watching it at each stage. So at stage 0, how many people have watched the video? 0, right? Because that hasn't happened yet. Stage 1, how many people watched the video? 1, that's Keisha, right? And then at stage 2, how many people have we added to the video list? Well, not including Keisha, just we've added 3, right? Then at stage 3, how many have we added? That is 9. Then stage 4, how many are we adding? 27. And then stage 5, how many would we add? Well, what's our pattern? We're multiplying by, so 81. So that's not on the list. There's no, we're going up that way, right? So is this a linear relationship? No. Right. So why is it not linear? How do we know by looking at the graph? All right, so since it's not a straight line, we don't have a constant slope, right? So we can expect that our equation is not going to be in that y equals mx plus b format. It's going to look something different. So is the graph a function? Yeah, right? So what's the quick test that we can use to determine if it's a function? The vertical line test, good. And so remember the vertical line test, we can take a straight line, and as long as our line is only touching one part of the graph, then it is a function. And so this one passes that vertical line test. For each x, there is only one y output. So what's the domain of this function? All right, so what's the domain? What does that mean? What's it asking for? All right, so our x-axis, which is in this case, as Tom said, our stages. So what would be some valid, is any number a valid stage number? Positive whole numbers, right? Because we're not going to have half a stage, right? So we need and we're not going to have -2 stage, right? We're not going back in time. It's either started or not. So the domain, how would we write that? All right, so if we write it as an inequality, x is going to be greater than or equal to 0 in whole numbers. Or any whole numbers greater than 0 works. Yep, that would work too. So as we've seen, we've had several different ways of wording that, and that works. Yep. as long as you're showing me that it's not a negative number and that you can't have a fractional stage. Yep. And that's what the x greater than or equal to 0 shows that it's positive. And then stated whole. But Tom said he chose natural numbers, which works. And Michaela had worded hers differently, so that works. All right, so the number of people who have received the video link at each stage form a geometric sequence. A geometric sequence is a sequence of values in which a non-zero constant ratio exists between consecutive terms. The constant ratio is called the common ratio and is typically denoted by the letter R. The common ratio is the value that each term is multiplied by to get the next term. So write the numbers of people who have received the video as a sequence. So that's kind of what we had started to do in that table. So in table 1, so stage 1 we had one person, we had Keisha, and then to that we added how many people? 3. And then to that we added 9. And then to that we added 27. And then to that we added, what was the next stage? What was stage 5? 81. And it would keep on going, right? So identify the common ratio, justify your response. So each stage, we had said when it said, what's your pattern? Each time we're multiplying by how much? All right, so could we write each of these numbers with a base of 3? Right? So 81 is 3 to what power? 27 is 3 to what power? 9 is 3 to what power? 3 is 3 to what power? And 1 is 3 to what power? 0. So I did 3 squared twice. Wait, 81 is 3 to what power? All right, questions? All right, so identify each sequence as arithmetic, geometric, or neither. If it is arithmetic, state the common difference. If it's geometric, state the common ratio. So arithmetic sequence we did at the very beginning of the year. So this is when you're adding the same number to each one. It'll be a linear function. So looking at A, B, C, D, and E, figure out, are you multiplying by the same number, which would give you the geometric sequence, or are you adding the same number, which would give you the arithmetic sequence? So let's take a couple minutes and look at those. So, do I have volunteers who'd like to do these? All right, Shannon. I'll do all of them. I don't know. I'll do C. Okay. I got C. Did I do it right? Okay. I'll still do it. I'll fix it up.
really turn up on here? Oh, that'd be nasty. You nasty. Oh. Get it. Really see it. Yes.
Right? Don't understand what that says. All right,
It's
so
n plus 1 squared, 1 plus 0 squared, 1 plus 2 squared, and 1 plus 3 squared.
all right, so here the pattern is n plus 1, so we're adding 1.
Like 0.
So 1 is 1 squared. 4 is 2 squared. 9 is 3 squared. 16 is 1 number squared. 4. So if you start with 0 plus 1 is 1 squared. And then 1 plus 1 is 4 squared. 1 plus 2 is 9 squared. 1 plus 3 is 16 squared. So you're adding 1 to your base and then squaring. That one was pretty. Alright. So your homework is going to be 11 through 14.